Hey everybody, I wanted to send you an example of another integrated problem with forces and motion. So today we're going to be looking at an ice climber during a dramatic rescue. So you and your buddy are climbing up this mountain when your buddy suddenly slips and he falls over this edge, and you guys are connected by a rope, and he starts sliding down a 60-degree slope, and he has a mass of 51 kilograms, and he's sliding on very, very slick ice. So for your buddy right here, we're going to say he's pretty much sliding on a frictionless surface that has a coefficient of friction of 0. So he's sliding without friction on the ice, and you guys are both moving down at 3 meters per second, and you are very smartly, you have your pickaxe out and you're digging it into the ice, and you also have your crampons. So you have a really high coefficient of friction of 0.85, but you guys are sliding at the same velocity, and you are so you're currently sliding 3 meters per second towards the cliff edge, and you are 16 meters away. So do you guys stop before going over the edge? And if so, where do you stop? If not, how fast do you guys both, do you go over the edge, and how bad is it looking? All right, so the first thing to do, right, when looking at a force analysis problem is usually to draw the free body diagrams. And remember that when we have a tilted surface, we often make the x-axis parallel to the surface, and the y-axis is perpendicular to that surface. So that's what we've drawn here. And remember that when you have a system of masses, in this case the mass of your friend, which is 51 kilograms, and the mass of yourself, which is 72 kilograms, you need to draw a free body diagram for each of them separately, because they each have different forces acting on them, right? You have friction acting on you, but we said this guy is sliding on very slick ice, so he does not have friction acting on them. So we need to draw separate free body diagrams for them, so let's go ahead and do that. All right, so what do we have acting on you? Well, you're lying on the surface, so you know there's going to be a normal force coming out, right? And you know that there's going to be tension because you're being pulled by your friend to the right, so tension is going to be acting to the right. And you know there's friction, and friction is going to be acting in the opposite direction of your velocity. So F of K is going that way. And then the weight, right? And we're on a tilted surface. We know gravity is going down, right? The weight is going down, but some of that weight is going to be acting in the x direction, and some of that weight is going to be acting in the y direction, right? We break it up into the components, and this angle of 10 degrees is actually going to be the same as this angle here, which means Wx is going to be m1 times g sine theta. We'll call it theta 1 for this angle, and we'll call this angle theta 2. All right, and Wy is going to be m1g cosine theta, right? All right, so we can draw those on there now. Why don't we go ahead and draw the components on there? The y component of the weight is going this way, and the x component of the weight is going in the positive x direction as well. All right, so let's fill out our free body diagram for our friend here. So we know there's going to be similar forces acting on him. There's going to be a normal force. We know there's going to be a y component of the weight, which isn't going to be very big because it's a steeper angle. And we know there's going to be an x component of the weight. And they're actually going to have the same equations here, just with a different mass and with a different angle of 60 degrees instead of 10 degrees, right? And then we know tension is going to be pulling in the opposite direction. And it's the same magnitude of tension that's pulling on you. All right, so now that we've filled out our free body diagrams, it's time to look at Newton's second law, because we're going to need to know what is the acceleration. Are we slowing down or speeding up? We don't even know that yet. We have our pickaxe. We're trying our best to slow down, but our friend is pulling us down. So we're not sure if our acceleration is going to be positive or negative even. All right, so let's write out some of Newton's laws. So we want to write out Newton's laws separately for each person. All right, so let's start with this guy. Okay, we'll write out Newton's laws. So Newton's second law for this guy. For M2, we have the sum of the forces, let's say, in the y direction. So what's acting in the y direction? We have the normal force, and we have the weight in the y direction, which is going to be negative m2g. The y direction is going to be cosine theta 2, which is 60 degrees. And we know we're not falling through the snow, we're staying on the snowbank or the ice wall. So the acceleration in the y direction is going to be 0. So we know the normal force for this guy is going to be equal to m2g cosine theta 2. Okay, so we solved that y, and we might not necessarily need to have done that, but we're being thorough. Now let's look at the sum of the forces in the x direction acting on this guy. So what do we have? We have the x component of the weight, which is m2g sine of theta 2, minus tension, because tension's pulling in the negative direction. That's going to equal mass 2 times acceleration in the x direction. And that's what we want to find out. All right, so if we look at this equation, right, we have two unknowns. We don't know the acceleration in the x direction, and we don't know the tension in the rope. So we're going to need to look at the sum of the forces acting on mass 1, acting on you. So let's start writing some of that out. So for M1, let's do the sum of the forces in the y direction for it first. So we just look at our graph. We have the normal force, and we have the y component of the weight vector. And just like with the other guy, we're not falling into the snowbank. We're staying on the snowbank. So we know acceleration in the y direction is going to be 0. So we actually kind of get a similar solution here for the normal force, except this time we're probably going to end up using it. Okay, so we've solved for what the normal force is acting on you, the climber number 1. Now let's look at some of the forces in the x direction. So what do we have? We have Wx and tension both acting in the positive direction. So Wx is the x component of the weight, which is sine, and tension's positive because this time tension's pulling in the positive x direction. And then we have F of k, friction, kinetic friction, acting in the negative x direction, trying to slow us down. That's going to equal mass 1 times acceleration, right? And we know that since the two people are linked up, acceleration of mass 2 in the x direction is going to be the same as acceleration of mass 1. All right, so we also have this friction, but we know, remember, that kinetic friction equals the normal force times the coefficient of friction. Right? And for this guy, the coefficient of friction is 0.85. So we can put that in there, and we solved for the normal force already. So let's go ahead and put that in there. All right, so let's check out what we got. Now we have this equation where we also have two unknowns, tension and acceleration. And when we did the free body diagram for the other guy, we also had the same two unknowns. So what do? We can make a substitution. We express one unknown in terms of the other. So why don't we add tension to both sides of this equation and subtract m2ax to get that tension is going to be equal to m2g sine theta 2 minus m2ax. And just like we usually do, we're going to make a substitution. We're going to substitute this and bring it down to there. So we get m1 sine, oops, we got gravity. Theta 2 minus m2ax minus m1g cosine theta 1 times mu k equals m1ax. So we have, now when we count the unknowns in this equation, acceleration is the only unknown. We want to get acceleration by itself, so we add m2ax to both sides. And we're going to have ax times m1 plus m2 equals, gravity is kind of multiplying by everything, so we'll just factor that out. m1 sine theta 1 m2 sine theta 2 minus m1 cosine theta 1 mu k. All right, so ax, we just divide both sides by m1 plus m2. And when we put in 10 degrees for theta 1 and 60 degrees for theta 2, 0.85 for our kinetic coefficient of friction, and I believe we said 51 kilograms was the mass of your buddy sliding down the hill, and 72 kilograms is the mass of you on top of the hill with your pickaxe. And when you plug in all those numbers, you should get that the acceleration is negative 0.287 meters per second squared. All right, great. So we've solved for the acceleration. Now we need to know, do we stop before going over the edge? So to revisit this, we're initially sliding at 3 meters per second, and we're 16 meters away from the edge. So we want to know, do we stop before going over the edge? So what I would do is I would say, okay, we know when we stop, our velocity is going to be 0. So how long is it going to take us to stop? So we can use this kinematic equation. And by the way, it's a really good thing that our acceleration is negative, right? Because that means we're going to be slowing down. We started off with this velocity, but our acceleration is going to be going that way, so that means we're going to be slowing down. So we do have at least a chance of stopping before going over the edge. All right, so why don't we assume that we do stop and figure out how long that takes. How far do we go? We can use this kinematic equation that the velocity, the final velocity squared, is going to equal your initial velocity squared plus 2a times x minus x naught. Should look familiar. And if we want to figure out this, how far do we have to travel in order for our final velocity to be 0? Okay, so we're going to have 0 equals 3 squared minus 2 times 0.287. And we'll just say x initial is 0. We want to solve for this unknown x. How far do we travel before we stop? So we can rearrange this equation, and x is going to equal 9 divided by 2 times 0.287. And when you crunch those numbers, that should give you 15.7 meters. Woo! That was close. So we stop 0.3 meters from the edge. We end up rescuing our friend and saving both of us from peril. That was a close one, you know, and if it was looking not too good, this guy probably would have just cut the rope and cut his losses, right? But he didn't have to do that. He rescued his friend, and we rescued him with physics, so we can feel good about ourselves. All right, so hopefully that was a useful video. Remember that when you have a system of masses, you need to draw a separate free body diagram for both. And you need to break up the forces, of course, into their x and y components when they're not aligned with one of your axes. All right, thanks for watching. See you soon.